let's first consider 2D supersymmetric sigma model. So let's choose M to be Riemannian manifold. And G mu nu of phi to be the metric, and phi mu are coordinate of M, which is the scalar field in 2D, and I goes from 1 to dimension, real dimension. Okay, so those are notations. Okay, and the Lagrangian density that we consider in 2 dimensions is starting with a metric. These are del and del bar on the worksheet, and then there is a kinetic term. I'm writing mu and using mu and nu to make sure that we're not just considering Kähler manifold anymore. We are considering some general Riemannian manifold, rho sigma, del bar phi rho psi sigma, and 1/2 of G mu nu psi nu bar del of psi bar nu plus gamma nu rho sigma del phi rho psi bar nu sigma. So psi without bar, the left mover, psi with bar, the right mover, and then there is the curvature coupling for Fermi interactions. Excuse me. So this is the Lagrangian, and the action is an integral of this Lagrange density over 2-dimensional space-time. So the task is to compute the Witten index, which is trace of -1 to the m e to the minus beta h okay, and where this is a fermion number. So since this is a supersymmetric sigma model, state can be divided into those with fermion number, odd fermion number, and even fermion number. And this is a fermion number parity operator. H is a Hamiltonian you can derive from this Lagrangian. Okay, and I'm gonna calculate this quantity in 3 ways today, and then compare. Okay, so the first method is just consider this as 2D sigma model, and then just calculate the Witten index directly. The second method is to put it on a cylinder with very small circumference and effectively reduce this program to 1-dimensional program and calculate Witten index for this 1-dimensional program. And finally, we reduced it to 0-dimensional space from 2 to 0, and then calculate it. And then they all should agree, because Witten index is quantitative invariant under continuous deformation of the theory. And then we compare. Okay, so first we do 2-dimensional calculation. So we calculate it in 3 dimensions, 3 ways. So A, B, C. So this is 2D calculation, 1D calculation, and 0D calculation. And we're going to compare these. So, so first calculation, A, is to calculate this directly for the 2D sigma model. But if you try to do that, there's a problem. There's a problem in doing that. And the problem is the following. So in order to actually do the Witten index, we need a continuum spectrum to make discrete spectrum. I apologize. Witten index well defined. We need a discrete spectrum. Okay, so here is what I mean. So the Witten index is defined as we saw. So there's a ground state, and then there are some excitation, E1, E2, E3, and then there is a eigenvalue Hamiltonian, and we distinguish that for bosonic state and fermionic state. And then I pointed out last time that there are equal number of states for the excited states, but there can be discrepancy for the number of ground states, and the difference is the Witten index. So this is a well-defined quantity as far as the spectrum is discrete. But there can be a situation where a spectrum can be continuous. So for example, suppose you have infinite. So suppose there can be a situation where, so one possibility is that when you have some kind of sigma model whose target space opens up, and the spectrum can sort of go down. So for example, the example that we can have in mind is that we consider a sigma model whose target space is a circle. When the radius of the circle goes to large, the Karuta-Klein mode, the momentum eigenstate around the circle, can have arbitrary small energy. So these energy spectrum can go down. And eventually it becomes continuum spectrum, goes all the way to zero. So you have a bosonic state and fermionic state. There's a continuum. So it becomes unclear how to match particular state here to particular state here, because there are infinitely many of them. And as you probably learned in sort of introductory course in mathematics, if you have infinitely many states, there can be many funny things happens. So for example, all the integers are the same as set of all integers are the same as all the fractions, but the number of fraction, a rational number, is less dense compared to irrational number, for example. So there are many funny things happening over here. And so for example, if you directly try to calculate the Witten index for theory like that, you get funny answers. For example, sometimes this can become even fractional or even irrational. You get all sorts of funny answers for this Witten index in this case. So you need to make, so if you, Witten index, calculating Witten index for this kind of situation is tricky. Calculating Witten index for discrete spectrum is much more well defined. So, but now, if we try to do the Witten index calculation for this theory, and so one way of doing it is to do the perturbation, which is to say that, oh, excuse me, just realized. So I was using phi for scalar use, I should have used phi. And then this is a function in general, phi. So if we try to do that, one way of doing it is to pick some particular value of phi and expand this Lagrangian in power of phi away from this particular value. So for example, if we try to sort of program this. So we have this Lagrangian which depends on phi and psi bar. Psi is a fermion, phi is a scalar field. So one way to try to do the perturbative calculation in this theory is to write phi as phi 0. So phi is a function of z bar. But then you can try to write phi as phi 0 plus some fluctuation, which can depend on z and z bar. And then try to expand this Lagrangian in power of this fluctuation. Okay? So you can certainly do that. And so you can certainly expand in power of this. And then linear term actually vanishes, and the quadratic piece gives you the free field, free massless scalar field. And then there are interactions between this and this, and then you can actually do the Witten index calculation. That seems to be fine, except there is one program, which is that there is actually continuous. So phi naught can take any value in M. So M is, I'm assuming, is some particular Riemannian manifold in some dimension, the target space of this sigma model. And for any point of M, we can do this expansion. Okay? If we are talking about quantum field theory in space-time dimension greater than 2, for example, 3-dimensional quantum field theory, 4-dimensional quantum field theory, it is perfectly fine. This is the kind of situation where we always encounter in spontaneous symmetry breaking. So for example, in standard model of particle physics that you might have seen in your course, in introductory course on elementary particle physics, there is a Higgs field. Higgs field takes from particular vacuum expectation value. The value is fixed, and that spontaneously break the symmetry of the gauge symmetry of the standard model of particle physics and give mass to quarks and leptons. That works. So the expectation value of the scalar field, like this particular value around which we expand this scalar field and do the path-of calculation, works in space-time dimension 3 or higher. But in 2 dimension, it doesn't work that way. That in 2 dimension, actually, when you do the path integral in 2-dimensional quantum field theory, you actually have to integrate over the vacuum expectation value of phi naught. You cannot take phi naught to be a fixed value. So there is a thing called the Coleman theorem. Coleman theorem says that there is no spontaneous symmetry breaking, in 2 dimensions. In quantum field theory in 2 dimensions, there is no spontaneous breaking of continuous symmetry. So, well, this is not quite symmetry. The shifting value of phi naught is not symmetry unless phi has isometry. But this is in similar spirit. That the idea of Coleman theorem can always, or if you apply the idea of the proof of Coleman theorem in this setup, what this means is that if we are talking about quantum field theory in 3 or higher dimension, we can fix the value of phi naught, but in 2 dimension we have to integrate over phi naught. Okay? So that causes a problem for this kind of situation, because what it means is that for each value of phi naught, there is a perturbative vacuum. There is a one parameter family of perturbative vacuum that we have to integrate over. And excitation around that has a very light energy. So that actually gives rise to the continuum spectrum like that, exactly the kind of situation where it's hard to do the calculation. Okay, so you can ask, well, so then how do I calculate Witten index perturbatively by expanding expectation value scalar field around the particular point? Well, what you can do is add a potential to the scalar. So you start with phi, and then for this Lagrangian, and if you expand phi to be phi naught, is phi to be phi naught plus del phi. So this is some fixed value. Then, for this Lagrangian, phi naught can take arbitrary value on the potential, on the manifold. So this takes a value in M. It's a coordinate on the manifold. But what we can do is add the potential. For phi. So that the value of the value of this phi naught can be fixed. That there's a potential, so the phi try to minimize the energy, and that fixes the value of phi naught. But we need to do it in a way that preserves supersymmetry. So supersymmetry requires the deformation we can do is to add a potential like this. Okay. So you have this term, and you have this term. Let me write it more clearly. So we have we deform the Hamiltonian, we hope deform the Lagrangian, so that it is of this form for some function h of phi. Okay, for some so this can be any smooth function on the manifold n. So you do this perturbation, okay? And the nice thing about Witten index is that I argue that Witten index is invariant under smooth deformation of the Lagrangian. So you can sort of turn on this smoothly, and the value of Witten index should not change. So, but this lifts the vacuum. This lifts a continuous family of phi. So this makes the calculation well defined. This is very similar to the quantum mechanical model that we considered in the last lecture, where we had this term of 1/2 of v dash square plus 1/2 of v double dash psi bar. You remember in the quantum mechanical model that we discussed last time. And this is sort of a generalization of that, where scalar field takes value on some higher dimensional model. Okay, so we can try to do the calculation of Witten index in this way. Okay, so this is a potential for scalar field, and you can think of this as a mass term for the Fermi. And so this lifts the continuum of the spectrum. Okay, so what this means is that the potential for phi is given by 1/2 of Gij del h del phi I. I guess I'm using straight phi. Del h del phi j. So that means that minimum of the potential at the point where derivative of phi vanishes. Okay, so you might remember the discussion we had in the previous discussion. In the last lecture, we had this potential, and we did this kind of things where we said that this corresponds to bosonic ground state, and this corresponds to fermionic ground state, and this corresponds to bosonic ground state. We do the same thing, but in higher dimension. Okay? So what you can do then is, suppose I expand, suppose you have a point. If so, phi naught is such that del h del phi at the phi naught is equal to 0, then we may consider expanding h of phi around it. Well, so there can be a constant term, but constant term does not matter because what matters are derivative of h, but let me write it over here. And then suppose you have this quadratic piece, and we can consider expanding around minimum of potential, which is this, so you can write it this way. I keep using curly phi. I apologize. I think that's my note. I apologize. I keep using curly phi. Need to remember. Mentally switch the notation. Plus order phi minus phi naught to the cube. Okay, so you can expand it that way. And so in the previous case, the question was whether the potential is growing or decreasing at the minimum, right?
Should it be V prime on the axis?
This is V.
Oh.
Because the V prime. Excuse me. Yeah, V prime. You are quite right. V prime. This was V prime. So a similar thing was H prime, right? Whether H prime is positively growing or negatively growing. But there are many directions to take derivative of. So what you need to do is then diagonalize them. So N is a symmetric real matrix, so you can choose a basis of phi to diagonalize it. And then the question of whether it's fermionic or bosonic in particular direction is whether eigenvalue is positive or not. If the eigenvalue is positive, you have a fermionic or bosonic state. If the eigenvalue is negative, you have fermionic state. So that means that the vacuum, the perturbative vacuum. So remember that in the previous case also, these were like perturbative vacuum. These are, each of these is a perturbative vacuum, but there can be instanton connecting between them, and they can be lifted. But Witten's index calculation is still true. So the perturbative vacuum at phi naught takes the value of tensor product of bosonic vacuum and tensor product of fermionic vacuum. Let me explain what I mean by that. So these correspond to positive eigenvalue eigenstates of M, and these are negative eigenstates of N. You see that suppose a dimension of N is N. Suppose you have n-dimensional target space manifold. Then this is n by n real symmetric matrix. You can diagonalize it. Suppose some of them have positive eigenvalue. For this direction, you have bosonic vacuum. For direction with negative eigenvalues, you have fermionic state. There can be a situation where eigenvalue vanishes, but then you want to actually deform this potential further to lift that zero eigenvalue, because you want the purpose of life of this potential is to lift all the vacuum, to lift all the flat direction. So therefore, we have to choose H so that the eigenvalue of M is either strictly positive or strictly negative. The positive one corresponds to bosonic direction, negative one corresponds to fermionic direction. The tensor product, right? Because it's a tensor product of fluctuation in n different directions in the target space. So then that means that the fermion number parity of this perturbative vacuum at phi naught is -1 to the number of negative eigenvalue of square the two derivative of phi. Hessian. So you calculate the Hessian of this potential function h at the stationary point of h. So you choose any smooth function on the target manifold M, and then you identify the stationary point of this smooth function, and then you calculate the Hessian, and you identify the number of negative eigenvalue of Hessian, and that gives rise to the fermion number part. Okay. However, there is one more thing we should consider. In general, if you choose a smooth function, it can have several stationary points. So for each stationary point, you have perturbative vacuum. Just like here, for this function, potential function b, if I take derivative of this potential function, there can be a few stationary points. For each one of the points, there is a perturbative vacuum. And it can be bosonic or fermionic depending on the direction of the gradient. So we have to sum over all possible stationary points. So that should give the formula. So namely, so here is a formula that this discussion gives rise to, which is that fermion number, so the Witten index for this system should be equal to phi naught, the number, the sum over, should be equal to sum over stationary point of this function and minus 1 to the number of negative eigenvalue of two derivative of h. Okay, so this is the formula. This looks like a rather surprising formula to me at first sight. When I saw this first time, I was a bit suspicious. And the reason I can be suspicious is that the left side is defined only for given manifold. So you give me some manifold, it can be two-dimensional manifold, sphere, torus, or something like that, or more complicated manifold in 3 or higher dimensions. So this formula tells you that I can choose any smooth function, h, and then just calculate, look at around the stationary point of that function and calculate calculate the Hessian and count the number of negative eigenvalues. And that should give you this Witten index. Is that me? Can I choose any smooth function? So, but this is actually correct formula, and so let me show you how the calculation works. So let me show you how the calculation works in two-dimensional case. For example, suppose you have a sphere. So this is 2D sphere. So let me just give you one particular example of smooth function on this sphere. So one possible smooth function is the following. So suppose I place some plane and calculate the height. So what from the plane to the point. What I mean is that you ask me to pick any point on the sphere and draw a straight line vertical to this plane and measure the height. And so that gives you h of phi, where phi is a point on this sphere. Okay? This is called the height function. And in fact, that's why I was using h to denote this potential. Okay? So then we got h is the height of this potential. Okay? So now then we can ask, well, where are these? Where are the stationary points? Well, you can see that the stationary points are at North Pole and South Pole. So that's where the height, this is where height maximizes, and this is where the height limits. And you can ask, well, what the Hessian? Well, here, so this is height is in this direction, right? So that means that in this direction, whichever direction you go, height decreases. So that means that eigenvalue of Hessian over here is both negative. So that means that the number of negative eigenvalue is 2. Right? And here it goes up in both directions. So the number of negative eigenvalue is also 2. Both are even. So that means that trace of -1 to the f is 1 plus 1, because there is 1 here, and this is 2. This is Euler number of sphere. Okay, so let me give you another example. So let's choose H. Let's choose more general thing. So let's choose some higher genus Riemann surface. And this is the height function. And again, I put some plane on it and measure the height from the plane to up. Okay, so you can ask, well, where are the stationary points? The stationary point, they are colored chalk. Yes. So stationary points are here, 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 right? So there are. So in this particular case, there are 8 stationary points. Okay. So what are the Hessians? Well, the contribution from here and here are the same as that of the sphere. So this gives you 2. This gives you 2. But how about here? You see that these are all saddle points. Namely, for example, if you look at this stationary point, in this direction, along the hole, the height increases. But perpendicular to this, height decreases. So that means the number of eigenvalues is 1. So here is 1, 1, 1, 1, 1, 1. So around each hole, there are pair of stationary points, for both of which the number of negative eigenvalues is 1. Okay? So that means that the trace of -1 to the f is equal to 2 minus 2 times the number of holes. Number of holes is called genus. So this is actually 2 minus 2g. And this is the correct Euler number, Euler characteristic. In fact, it's a mathematical theorem. So this is actually a demonstration, but there is a mathematical theorem attributed to Morse. It is called Morse function. That if you the statement is that for any smooth function h on M, the sum of phi naught, which is stationary, of -1 to the number of negative eigenvalue of the Hessian is equal to Euler characteristic. Okay. And in that case, h of I is called Morse function. Okay, so this is one of the beautiful statements in differential topology. But you see that there is a physical derivation of this statement by doing this kind of Witten index calculation. Okay, so this is calculation number 1. So the calculation number 2 is a reduction to one-dimensional problem, which gives you a direct relation between this type of Witten index calculation and Euler characteristics. So the calculation number 2 is a reduction to a one-dimensional problem. Again, this makes use of the property of Witten index, which is the statement that it's invariant under deformation. So what I do is that we can put this sigma model on the cylinder, and when the cylinder is very, the circumference of the cylinder is very wide, it goes to the two-dimensional flat space, reduces to the Witten index calculation in flat space, flat two-dimensional space. But then you can actually shrink the size of the radius to be very, very small. This process is adiabatic, and the value of Witten index should not change under such deformation. And eventually, you can make the size of a circle, the circumference of the cylinder, as small as possible. So essentially, the problem quantum field is reduced to one dimension. So that means that the action, which was originally integral of the Lagrange density, if the Lagrangian depends, so what's going to happen is that the Lagrangian contains a term like this, 1/2 of del phi I, del bar phi j, g I j bar, mu nu, actually, mu nu, plus fermion term. But if the direction, the circumference of the cylinder direction becomes smaller and smaller, it costs lots of kinetic energy to excite phi in that direction. So that means that the two-dimensional circumference becomes thinner and thinner. It costs a lot of energy to have non-trivial dependence of phi along this direction, because this is going to blow up. The Fourier mode diverges if the radius becomes small. And so that means that the excitation along this direction is suppressed. So we can essentially assume then, in the limit when the circumference becomes small, the phi stays constant around the circumference. And that's how the problem reduced to one-dimensional. So that means that this essentially becomes the length of the circumference of the cylinder. So I'm assuming the two-dimensional space now becomes cylinder. And then circumference of the cylinder times just one-dimensional integral. So this direction is t, and this direction is L. And the dt of 1/2 of g I j of phi dot I, phi dot j, plus 1/2 of g I j, psi I, d dt, psi j, plus gamma j k l. Oh, mu. I was using mu. Sorry. Mu nu. Mu nu. Mu nu. Mu nu. Mu. 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 Rho sigma. Psi. Phi. Dot. Rho. Psi. Sigma. Etc. Okay, so we have this kind of problem, right? And so now this becomes one-dimensional quantum mechanical problem. Okay, so it's easier to deal with. And we can do that because the calculation we are doing is not sensitive to the circumference of the cylinder, because it's a weight index calculation. Okay? But nice thing about this is once we get into this program, then we can actually understand the Hilbert space of this system much better, because this is a one-dimensional quantum mechanical problem. We know how to solve this problem. Okay, so let's try to solve this. The reason I do that is because what we want to calculate in the end is trace minus 1 to the f e to the minus beta h. So to do this calculation, we need to know what is the space for which we are taking trace of, namely what the Hilbert space is. So let's try to understand the Hilbert space. So how do I understand the Hilbert space? Well, there are a variety of ways. One is to do the canonical computation. So we have Lagrangian. So we have time derivative of scalar field, time derivative of fermions. We canonically quantize it, which means that we identify the momentum conjugate to boson and the momentum conjugate to the fermions, right? So let's look at the momentum conjugate to fermions. Well, so So this is fermion, and you have time derivative. So momentum conjugate is psi bar. So that means that canonical constellation give rise to this cohabitation relation. Psi mu, psi bar nu is equal to G mu nu. And the psi commute with each other. And psi bar commute with each other. Right? So this is the canonical cohabitation relation. Okay, so this is what we learn in undergraduate quantum mechanics, right? So first we have this. So what we can do is first define the vacuum to be annihilated by all the psi's. And then what you do is to build a Hilbert space starting with the vacuum, excite psi's once, excite psi's twice, all the way to excite psi's where n is the dimension of n. Okay, we can do more than that because there are only n fermions. And fermions are anti-commuting with each other. So if you have two identical fermions, then it vanishes by Pauli exclusion principle. Right? So therefore, this is all the excitation you can have for fermions. Okay? So I have quantized the fermion. We have to quantize boson. Bosons. For bosons, you have phi, and its canonically conjugate is phi dot, and that is the derivative of phi. So therefore, the Hilbert space of phi is a space of square integral function of phi, and for each direction of so what it means is that for each one of these fermionic states, you can multiply. For each one of these, you can multiply some function of phi. So that means that the Hilbert space consists of the fermionic vacuum multiplied by some function of phi. So this is a fermionic vacuum defined here, or some fermionic vacuum multiplied by phi. One excitation of fermion multiplied by phi, but there are n different directions. For each direction, there are different functions, so you can index them by mu. You can also have a mu nu of phi, psi bar nu, psi bar nu. And there are two pairs, a pair of indices, so that means that you have a square integral function of phi with two indices. And it goes on, and it goes up to n. And that's all you have for Hilbert space. This is the entire Hilbert space of the sigma model. Okay, so basically you have 2 to the n functions, where n is the dimension of the target space, and each function is a function or vector or tensor of the scalar coordinate phi. Okay, so that's all you have. Okay, and now if you have learned the differential geometry, some introductory course of differential geometry, you might have noticed that this space of all these is actually in one-to-one correspondence to the space of differential forms. Namely that you might have seen something like a mu1 to mu k dx mu1 wedge dx mu to wedge dx mu k. So if you study, for example, textbook of Robert Walsh, general relativity. For example, there are a couple of GR people here. Or if you have taken some advanced course in geometric methods in physics, you might have seen differential forms. And you can see that there is a one-to-one correspondence between differential form and the state in the Hilbert space. So the identification is such that, so you can actually write a table. So fermionic vacuum zero correspond to just 1. And then multiplication of psi mu correspond to the multiplication of d mu. And the multiplication of psi mu correspond the other way. Yeah, multiplication of psi mu correspond to the Hodge dual operation. So you can have this kind of table. Okay? And in fact, you might have seen that physicists use the term Grassmannian to discuss a variable like psi. But the mathematical reason for this is that these are actually not naturally associated to the Grassmannian manifold. So actually Grassmann is the 19th century mathematician who studied geometry of projective space, etc. And then this kind of notation naturally appear from this context. And then that's how these are built. Okay? So, but you see that you can, so now why am I doing this? Because I want to calculate this. And we have understood where we should be taking trace of. We should be taking trace over the space of differential form on the manifold. That's where we should be taking trace of. What is -1 to z? What is the minus? So we have to decipher this. So the Hilbert space is a space of square integrable differential forms. What is F? Well, there is identification between fermion creation operator and annihilation operator and multiplication of dx or removing of dx. So that means that F is actually the number of dx in the differential form, namely the degree of differential form. Okay? So that means that, for example, these are fermion number 0, these are fermion number 1, 2, 3, etc. So -1 to them means that you add 1 to odd forms, -1 to even forms. What is H? What is H? Okay, we need to understand what is H. Because this is supersymmetric system. So in order to understand H, we need to first understand what the supersymmetry is, because Hamiltonian is a square of supercharge. So let's first study how supersymmetry works in this thing. I think eventually I will pinch my finger in with this blackboard. Actually, they repaired this lecture hall. In the previous lecture hall, once actually the blackboard came off while I was trying to lift it or lift it down. It was very dangerous blackboard. I think I'm glad that they fixed it. So let's look at the supersymmetry. Of this one-dimensional sigma model. So we have this Lagrangian there, right? So we have this Lagrangian there. So we can actually see what kind of symmetry preserves this Lagrangian, and it's easy to find out. So you can Yeah, you can write it in this way. I dot I plus I gamma. Oh, not I again. Mu. There is a hazard of changing notation as you go. Okay, so this is supersymmetry transformation. Now, so we want to understand what H is, but H is Q square. So we need to understand what Q is and Q dagger. Okay, so we can and this epsilon is a spinner in one dimension, which parameterizes supersymmetric, and but we know what how the canonical consideration works. So we can actually write down the supercharge. So what we can do is that we can do Nader procedure. But we can apply Nader procedure. What it means is that we upgrade epsilon to be t dependent, and then look at terms that are proportional to epsilon dot, and that gives rise to supercharges. Q, which is equal to I p mu psi per mu, where p is minus I of del phi I, and then Q dagger is minus I p mu psi mu. So you can see that Q is equal to P, which is derivative, and psi is a multiplication of differential form. So what does it mean? Well, Q is equal to minus IP mu, but this IP mu is equal to derivative with respect to phi mu. And then we have psi per mu, which according to the identification corresponds to multiplication of dx mu. So namely, you take derivative with respect to the so this is actually d. I should have written d phi mu. Yeah, so maybe I should do that. So I should have identified this as phi, d phi, d phi. Maybe I should. Okay. So do the global replacement. So that means that this is actually exterior derivative operator acting on the differential form. And of course, Q dagger is a Hermitian conjugate of this, which means that it's a D star. D dagger, which is the star D star. So this maps N form, K form to K plus 1 form. This maps K form to K minus 1 form, right? And Hamiltonian is Q dagger, which is D dagger plus D dagger D. So this is the Lichner-Horowitz Laplacian acting on the differential forms. Okay, so you can see that this is nothing but this Laplacian operator. So what this means is that when beta goes to infinity, the h e to the minus 8 beta h projects onto delta equals 0 eigenstate. So namely, the harmonic differential forms that in the delta equals 0 correspond to d equals 0. So the state with delta equals 0 correspond to d omega equals 0 and d dagger omega is equal to 0. And these are like harmonic forms. And then this is a standard statement of differential topology that the number of zero eigenstate of the Laplace operator for degree D differential form is this Betti number. So let me write it out. So the number of delta equals 0 eigenstate at degree number of delta equals 0 degree K differential form is BK, which is the case Betti number. Okay, and so therefore the trace of minus 1 to the e to the minus beta h is equal to alternative sum of Betti number, and this is Euler characteristic of M. Okay. So therefore, combining the result A and B, we have shown that if you sum over H stationary of minus 1 to the number of negative eigenvalue of Hessian is equal to the Euler characteristic. Okay, so this is what we just showed. For any smooth function H. Okay. Okay. So this is nice result. So it's rather unexpected. It gives you connection between choice of smooth function. So that means that you cannot choose any smooth function. Somehow the choice of smooth functions is restricted. The very fact that H is smooth give you this kind of global restriction on the property of stationary point of H. Okay. So finally, we can consider the same calculation, but reduce it to 0 dimension. We can reduce it to 0 dimension and then give you another calculation. So what I do is that, for example, I can choose the 2D space to be on sphere of radius r, and then take r to be small. And it's a sigma model, so that means that it is a map from this space to some manifold M. This phi. And but if the radius becomes smaller and smaller, this phi should become a constant one. So that means that the path integral for the calculation, you can ignore all the derivatives. Namely, that so in one-dimensional case, the Lagrangian was, well, we can even start with 2 dimension, but well, maybe we can start with 2 dimension. So 2-dimensional sigma model started out with the following form. So the action was the integral of in 2 dimensions of 1/2 of Gij del phi I del bar phi j plus 1/2 of I of Gij psi I del bar psi j plus gamma mu nu sigma del bar phi rho psi sigma plus blah blah blah. And then you have 1/8 of r mu nu rho sigma psi nu psi nu psi rho psi sigma. So this was the Lagrangian. But if you take this two-dimensional space to be this two sphere, so phi is a map from this two sphere to the target manifold, and takes those two spheres, we should radius of the two spheres to be smaller and smaller, which we can do because Witten index calculation is invariant under continuous deformation, in this case of the radius of r. But if you take r to be small, then it costs you a lot of action. This becomes larger and larger because it has a derivative. If you take for any non-zero mode, if the radius becomes smaller and smaller. So that means that the excitation in this direction can be ignored. So we can remove this. We can remove this derivative. We can remove this derivative. And same is here. So the only thing that is left is this. So therefore action is actually equal to the volume of S2 times some constant fermions. And of course, R depends on phi, and then you have fermions. So phi and psi mu and psi bar are all constant. So you just have finite dimensional, so past integral becomes finite dimensional integral. So namely that all we have to do, so originally we were doing this functional integral of phi deep psi bar e to the minus s, and then we have to insert minus 1 to the f, which makes it supersymmetric. So we do supersymmetric calculation. So in order to do Witten index calculation, we need to do this kind of past integral. But then it can be approximated in this limit by just ordinary integral, n-dimensional integral of d phi, n-dimensional integral of d psi, n-dimensional integral of psi bar, e to the minus of 1/8 of the volume of S2 times r mu nu rho sigma of phi psi bar psi mu psi nu psi bar rho psi bar sigma. You just do this integral. Okay? Now this integral is straightforward to do the calculation, and then what you do is okay. So what you have to do is that you have this integral. And then we expand it. So namely that we have 1 minus 1/8 of volume of S2 times r mu nu rho sigma phi psi mu psi rho psi nu psi rho bar psi rho bar sigma plus 1/2 of this thing squared. And then, so you do this Taylor expander of the exponential, okay? And then do the past integral for fermions. Now, past integral for fermion is easy to carry out because if you have this, first of all, if you have fermion number, so you have to insert some number of fermions. Suppose you have k of them, okay? So then what we can see is that is that if k is not equal to n, it vanishes. That's the rule of the Grassmannian integral. The rule of Grassmannian integral is that for each psi mu, it is equal to 1, and then d psi mu 1 is equal to 0. So that means that unless each integral direction is matched up with the integrand, it vanishes. And when k is equal to n, then it's actually epsilon tensor. Okay, so that's a rule. So that means so from this you can immediately see the calculation, because you can see many things. For example, this is equal to 0 unless n is even. Because if n is odd, well, there are only even number of sides and even number of side bars. So if n has to be even, otherwise this can never happen in this expansion. But if n is even, then what happens is that this is proportional to d n to the phi. And so if n is even, and if n is 2n, so basically this is equal to r to the n, or n over 2. Maybe we can just write n over 2 where n is even. Oh, so sorry, n is odd. I'm sorry. N is odd. And then if this is oh yes, so maybe it's confusing way. So if n is odd, it vanishes. If n is even, n over 2 is an integer, so you can consider r to the n over 2, and then contract indices appropriately by epsilon symbols. So the more precise formula is epsilon of mu1 to mu n, and epsilon mu1 to mu n, and r mu1 mu2 mu1 mu2 r of mu of n over 2 minus 1 mu of n over 2 mu of n over 2 minus 1 mu of n over 2. Yeah, I think this is the correct formula up to some combinatorial factor. This is the answer. And so this should be equal to the Witten index, which is Euler characteristic. Okay, so that's the answer. So this tells you that this is actually equal to 0 when n is odd, and is equal to integral of r dot 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 r when n is even. And this is the correct answer. This is called Gauss-Bonnet theorem. That Euler characteristic can be expressed in terms of integral of product of Riemann curvature. Okay, you can easily see that when n is odd, when the dimension is odd, then this vanishes, because there is actually a relation that b of k is equal to b of n minus k. So that means that when k, namely the dimension of n, if n is odd, then you can always pair b here and this with kind of contributing with opposite signs, so they cancel. So Euler characteristic always vanishes in odd dimensional space. But from Gauss-Bonnet theorem, we can also see that because there are no ways to construct Riemann curvature to make it invariant. And in even dimension, it's a very interesting formula that this is not in general non-zero, and that non-zero value is calculated by integral of Riemann curvature. For example, in two-dimensional space, for example, there is only one r, and basically what it means is that the Euler characteristic on two-dimensional surface, which is 2 minus 2g, is given by integral of scalar curvature on that surface. This is actually a generalization of what, this is a special case of what is called index theorem. For which such global topological quantity like Euler characteristic can be expressed as an integral of local quantity such as Riemann curvature. Okay? So there are actually many examples of index theorem. Those are all very interesting and very useful. For example, when you study quantum field theory, you encounter lots of funny phenomena such as anomalies, zero mode or path integral, etc. And those can be captured and calculated using index theorem. And this is the simplest example of such demonstration. Okay, so that was all I wanted to tell you about this Witten index calculation. So this more or less completes my discussion of sort of more of mathematical property of supersymmetric sigma model. So now I would like to get back to the use of this geometric method to study string compactification on Calabi-Yau manifold. Now, in fact, the reason I spent the whole lecture today, almost all the lecture today, on the Euler characteristic calculation, is that this is going to be the start in our discussion of Calabi-Yau compactification of heterotic string, as we will see. Okay, so I have only about 8 minutes left, so what I can do in 8 minutes. So I would like to start introducing how we sort of even consider producing four-dimensional world with low energy spectrum, which looks like that of the standard model of particle physics. So this is the first attempt. So this is a famous paper by Candelas, Strominger, Candelas, Horowitz, Strominger, Witten, please excuse me, that appears in December of 1948. And so that was one of the significant papers appeared in that paper. That year, superstring revolution started with a famous work by Michael Green and John Schwartz, discovering the anomaly cancellation mechanism of superstring theory that made it possible to introduce chiral fermions in string theory. And then there was the construction of heterotic string. That was followed by this Calabi-Yau compactification of heterotic string that appeared in December of that year. So that's what I would like to talk now. Heterotic string. On Calabi-Yau space, which means that we are considering three-dimensional Minkowski space with signature 3 space at one time times the Calabi-Yau manifold. Complex three-dimensional real 6-dimensional Calabi-Yau manifold. And then understand how you can actually extract some low energy physics from this construction. We'll be considering the situation where this compactification preserves supersymmetry. Our world does not, in low energy world does not have supersymmetry, so supersymmetry should be broken eventually. But here we are considering the more idealistic situation where supersymmetry is there. And then we'll separately consider how supersymmetry can be broken. So, heterotic string on the 10-dimensional space has n equal 1 supersymmetry in 10 dimensions, which correspond to 16 real supercharges. Now, by compactifying it on Calabi-Yau manifold, we will inevitably break some supersymmetry, but preserve some. And the natural amount you can preserve for Calabi-Yau compactification is the 4 real supercharges, which correspond to n equal 1 supersymmetry in 4 dimensions. Okay, so that's the situation we'd like to consider. Preserving this minimum amount of supersymmetry is convenient because without supersymmetry, we cannot guarantee that Calabi-Yau manifold is actually solution to string equation motion. But with supersymmetry, as I explained in the previous lectures, that we can guarantee that, for example, the scalar and complex structure of Calabi-Yau are not renormalized. So therefore, we can actually get some exact statement out of it. So for example, the number of generation of what can become quarks and lepton can be calculated exactly. Without supersymmetry, these numbers are guaranteed to be exact. So there is a problem with that. Okay, so what are the conditions to preserve supersymmetry? Well, I have already discussed the condition. That's how actually we got the Calabi-Yau manifold. But let me briefly remind you how we get it. So the idea is that 10-dimensional theory has local supersymmetry. So 10-dimensional theory, the low energy effective theory, in 10 dimension has n equal 1 supergravity. So you have a metric, you have gravitino, and then you have dilaton. So this is gravitino, and then this is dilaton. And then plus you have n equal 1 super Yang-Mills, which has gauge field and super partner gaugino. Okay. I guess the notation is that there is a dilatino here, and then there is a super partner chi. So chi is not Euler characteristic. Chi is a super partner of gauge field here. And we can write down supersymmetry transformation. So let me actually end it now here. So del psi mu is equal to del mu of epsilon minus 1/4 of h of mu epsilon, and del lambda is equal to minus 1/2 of d slash phi times epsilon plus quarter of h of epsilon, and del chi is equal to minus 1/2 of f times phi, where these f and h's are given by the field strength for the gauge field and field strength of unsymmetric 2 form in the NS sector that we discussed, but appropriately contracted with Dirac matrices. So let me just briefly tell you that Lagrangian for bosonic part of the system, it contains Einstein-Hilbert term and the kinetic term for the field strength of this unsymmetric tensor field, and field strength for the Yang-Mills field, and the kinetic term for the dilaton, right? And this H is a 3 form, so totally unsymmetric 3 form. So let me just write this as H is equal to 3 factorial of dx mu, dx nu, dx rho, which is equal to dB. So this would have been the natural 3 form. But the wonderful insight of Green and Schwartz is that actually there is a possibility of Chern-Simons term. Actually, I will tell you more about that in the next lecture. Let me just briefly introduce the notation. So you can actually add this what's called Chern-Simons term, because this is 3 form. And this actually plays a very important role to canceling anomaly in 10-dimensional heterotic and type 1 string set. And so this was the sort of key of the Green-Schwartz mechanism. So, but this will also play an important role in our analysis of heterotic string compactification on Calabi-Yau manifold. Now I just ran out of time, So here I just started to introduce you to the discussion of Calabi-Yau compactification, and in the next lecture I will fully develop this Calabi-Yau compactification description, and then see how a variety of feature of Lorentz effective theory can be derived from this construction. Okay, so that's it for today. Thank you.